introductions. I'm Je-Hyung from UNIST, and today I want to talk about the temporal and spatial shaping of single photon from the semiconductor quantum dot. So this work is done with a collaboration with Professor Wax. Professor Wax at the University of Maryland. And I want to start with the photon-based quantum information processing. So photon provide important carrier for quantum information processing, and it can generate quantum bit based on their lots of degree of freedoms, such as time beam, polarizations, and path informations. Also, you can use orbital angular momentum or the spatial mode. And the photon has many advantages over other qubits. So as a flying qubit, we can deliver the information over a long distance. They are merely interact with the environment, and we can easily create entangled photon state. And we can also achieve the quantum entanglement between separated spins. And also, more importantly, we already have a well-established linear optics and detectors to manipulate the quantum state of photons. So the key would be how to generate and control this quantum light. The more popular way would be using the nonlinear medium and the lasers to achieve spontaneous parametric down convergence. So we can achieve the entangled photon pair and squeeze state. But they provide the quantum light, but randomly. So alternative way would be use the isolated quantum particles such as trapped atoms or ions. But it requires the sophisticated, complicated trapping system. So another way is already the Professor Wax explained very well. So we have an alternative platform in solid. So quantum dot or the defect is representative examples. They can provide the quantum light from a chips. So that is very attractive. So also we can control this light using the well-known mirror, lens, beam splitter, and wave plate. We can manipulate their quantum state. Also, we can use the nonlinear effect from this bulk optics. And instead of this bulk optics, so we also have we can control the light from our chips. So we have a cavity. We can make a waveguide and cavities and integrated circuits. And if you want to use, we can also use the fiber optics. So thanks to the lots of effort from many groups, there have been huge advances in the solid-state quantum emitters communities. So nowadays we have a single photon with high purity and high indistinguishability with high brightness. So these data from these reference papers show it compared the conventional SPDC sources with solid-state quantum emitters. These black data show that represent SPDC, and it shows the inherent trade-off between the brightness and G2, also the indistinguishability for these SPDC sources, while the solid-state quantum emitter, in principle, it can go this way toward improvement of both brightness and G2, also brightness and indistinguishability. So not only for single photons, the quantum dot can generate entanglement photon pairs using biexton-exton cascade recombinations, and this entanglement photon pair can be nowadays they can be beat the entanglement photon pair source from SPDC, the blue data, but the quantum dot can go toward this way. So it seems this community is doing very well and shows strong potential as a future quantum light sources. And you can easily find many good results from these communities. So single photon with high purity and indistinguishability and entanglement photon pairs. And also the high temperature operation is possible, but that is not all material, but certain material can do this. And some quantum dot can also do telecom wavelengths. And spin photon quantum, using the charged quantum dots, spin photon quantum switch or transistor is available. That was the main topic of Professor Wax. And having all these fascinating technique. People try to apply it to certain photon-based quantum applications, such as single photon hardware, quantum key distribution and teleportations, and photon-based quantum simulators. So we can have many nice, promising results. But unfortunately, all of these results, they are all based on the single quantum dot. But considering the future scalable quantum system, we may need multiple quantum emitter and their quantum interactions. So, but that is quite a huge challenge to have multiple identical quantum emitters. And there is lots of effort to tune the wavelengths of individual quantum emitters and position of individual quantum emitters. So that is one huge topic in this community, but that is not a topic I want to talk today. But today I want to discuss another important aspect of single photon from these quantum emitters. That is temporal and spatial modus shaping of single photons. Ideally, having the symmetric Gaussian like the temporal and spatial shaping profile would be very nice to achieve the quantum interaction and quantum interference more efficiently and with high fidelity. Also, having such symmetric mode profile, that they are beneficial to have a high tolerance of mode mismatchings. But although the single exton from single quantum dot, it can produce single photons on demand, but inherently it is quite difficult to produce the symmetric temporal profile. Like this is a decay curve of single exton, and you can see here very fast picosecond lifetime with quite relatively long the nanosecond decay times. So converting this asymmetric profile into the symmetric profile is quite difficult, but to realize, to modulate the temporal profile, we use the engineer the exton dynamics. So the key was utilizing multi-exton complex instead of the extons. So bi-exton would be the well-known example of multi-exton, and charge exton is another multi-exton complexes. But we can consider even more high number of extons. So by exciting the high power laser, we can create lots of carrier, and it will form the multi-exton in a single quantum dot. And with time, they show cascade recombination, and eventually they will reach into the single exton state and emit the single photons. So through this process, it takes time. So it separates delay the single exton recombinations, and we can model this time delay with a multi-exton model. So the mu represent the average exton numbers. With small mu, like the almost single extons, so we can see the typical decay profile of single extons, but by increasing the number of extons, you can see the slow down the lifetime, also the temporal shift of this decay curve. In experiment, we can do this temporal shift, temporal modifications by applying the high power lasers. You can see that with increasing the laser power, P0 is the excitation power of single extons in a single quantum dot. And you can see the slow lifetime and temporal shift. These blue areas correspond to the single exton, while the red color is background emissions. Because we use high power lasers, there is lots of background fluorescence from the samples. So anyway, we can control the temporal retardation of single exton with the excitation power, and we can deform the lifetime of the single extons. But that would be not enough, although we can achieve the nanosecond long lifetime, but to make a symmetric temporal profile, we also need to shorten the decay profiles. So for that, we use the prosthetic enhancement. Here is a photonic crystal cavity, low Q cavities, and here is quantum dot, and there is a spectral detunings. And such a detuning can be engineered by this kind of method. Here we flow the nitrogen gas at low temperature that frozen the samples and shift the cavity mode. And as a result of engineering the cavity detuning, we can control the decay dynamics. So now we are quite happy because we can control both rise and decay dynamics of single extons. So combining both technique of multi-exton and partial effect, we can generate the single photon with Gaussian-like temporal profile. So this is nice, but major concern here is we use high power lasers. Actually, that is about the 100 times high power than typical excitation powers. So it creates lots of background emission. You can also see here, all this emission is from background. That ruins the G2 value, so single photon purity. But thanks to the temporal separation between single photons and this background emission by the retardation time, we can selectively filter out the single photons. So without temporal filtering, the G2 is as high as 0.5, but proper temporal filterings that remove these background emissions, it can improve the G2 value. So by widening this time window, we can achieve the quite low G2 value, even at very high excitation power. So this is the part of temporal shapings, and the second part would be how to achieve the optimize the spatial mode from the quantum dot. In particular, we are considering to coupling the light into the fibers, but the fiber, it has a NA, it has really small NA around 0.1, so coupling the light into the fiber from the quantum dot, it is quite difficult. Previously, there is lots of effort. The direct integration can be done just just attaching the single mode fiber into the chips, but we can guess how low the coupling efficiencies. Alternatively, we can consider add intermediate optic system here, so we can mediate the mode mismatching between the quantum dot source and the fibers. And another new way that Professor Wax already explained, adiabatic coupling, it guarantees really high coupling efficiencies, near unit efficiency. But in terms of the practicality and the mechanical stabilities, having such long tapered nanofiber, it is quite difficult. Also, the cooling this system, it is another painful way. So if we can have certain devices, thin devices, which can be stick on the fiber core, it will be nice. The bullseye will be the one good example. It has a very thin membrane structures and enable the Gaussian profile, but considering the small NA of a fiber, mode mismatch is still large, so the collection efficiency is quite bad. So we deform this kind of diffraction optics by replacing the rings with the holes. So with the holes, we can add another degree of freedom we can control. So it can, basically all these devices, it use a constructive destructive interference, and having one more degree of freedom, we can induce more constructive, more destructive interference to focus, to emit the light into the very small angles. So this is a far field pattern. You can see the emission comes out within very small angle, and the intensity profiles. So bullseye has some high order emissions, but photon shift, there's no such thing with narrow angles. So having these kind of structures, we were successfully, this is simulation result. You can see the collection efficiency is as high as 50%, even though we consider fiber NA 0.1, that is much higher than the conventional bullseye structure, less than 20%. And experimentally, we fabricated these kind of devices and attached to the fiber core using this kind of transfer system. And this is integrated quantum dot devices into the single mode fibers. And this is magnified image. You can see our devices, and the red color light is from the opposite end, the laser from the opposite end. So this is the entire system. So it's very nice. We have a single photon device. This is a plug and play devices. For having the single photon, we don't need any optical alignment. So we can just send the laser through the fiber and collect the signal through the fibers and just have the single photon at the end of fibers. So this is nice. You just need to plug in all the parts. But the quantum dot requires low temperature to emit the single photon. But if we can also apply the same technique for the defect, which work at room temperature. Then you don't need this kind of cryostations. And this is a spectrum and G2 values. So let me summarize my talk. So we try to optimize the temporal and spatial mode profile of single photons. So we engineer the dynamics, and we develop new type of the diffraction optics to have the optimized Gaussian profiles. And this kind of approach will enable some more practical devices from the quantum dot samples. You just need this kind of things without any alignment. You can send the exact system, and you can collect the single photon signals. So this will we hope this can serve certain the source through the fiber network. And again, the quantum dot not only the single photon source, it can also provide the quantum memories. So it can provide the important hardware for future quantum network. So this, thank you for your attention. This is group members, and the work is done by the collaboration at the University of Maryland. Thank you.
Okay, thank you, Professor Kim. We have one question here already. Can you apply your temporal and spatial mode shipping technique to the same device at the same time?
Oh, sorry again. So the temporal controlling the technique for same device.
Yeah, can you apply your temporal and spatial mode shipping technique to the same device at the same time?
Yes, true. Actually, yeah, that's true. There's no problem. So actually, the previous work is done with the photonic crystal. This work is done with the photonic crystal cavity, like this L3 cavity with a low Q cavity, and we can apply the same technique with a bullseye structure or the modified bullseye structure. Then it is possible to have the both the temporal Gaussian-like temporal and spatial shaped single photons. But actually, it already provides such a source because the L3 photonic crystal cavity higher order mode M3 mode already generate the Gaussian-like far-field patterns.
Okay, thank you. Thank you again, Professor Kim. I think we should stop here and finish the first session.